Hello. This webcast is about factor analysis. And I thought before getting into the SPSS stuff, we would give you a little demonstration of what a factor analysis does. And to do this, I've enlisted the help of my glamorous wife, Zoe. Sometimes when you collect large amounts of data, you have lots of variables. Now, these are balls, and these are special balls because they are representing variables that you might have created. Oops. To get a 3D effect for those of you watching in 3D. There you go. These balls are very variables. So we have 3 variables. Now, these variables are like a mass of confusing information because there's too many of them. So what we try and do with factor analysis, we try to reduce lots and lots of variables into a set of linear components, and hopefully there's less linear components than there are variables. So we can take out 3 variables and hopefully end up with slightly less linear variance. So Zoe and I are going to represent linear variance, and to do that, or factors, and to do that we are going to wear silly hats, because in the real world, factors, although they're statistical entities, they do have stupid hats on. So I'm going to be factor 1. Zoe is factor 2. Now what happens is we've got these variables, and these variables are going to kind of stick to the factors. So what we're trying to do is reduce the variables down into like these underlying factors. So we need to know which factors exist and which variables are kind of associated or attached to which factor. So you can kind of imagine, you sort of throw a variable up in the air and hopefully it sticks to one of the factors. So that means that variable, it likes Zoe more than me. So when, well, as most people would. So when you're evaluating which variable goes with which factor, it's kind of like saying, well, where does it have the stronger association? Which factor would it like to attach itself to the most? So our first variable, it wanted to attach itself to Zoe a bit more than it wanted to attach itself to me. So we could then look at the second variable, and whoa, it wants to attach itself to me rather than Zoe. So it has a kind of a stronger affinity to me than it does to the other factor. And then we have our third variable, and doesn't want to attach itself. We have our third variable, and that wants to attach itself more to Zoe than to me as well. So we've got 2 variables that are kind of loading heavily onto Zoe's factor. So they slightly prefer Zoe's factor to me. They have a stronger affinity, whereas one of the variables has a stronger affinity with me than it does with Zoe. Now, of course, in real life, what happens is the variables load slightly onto the factors kind of are intrinsically linked in some way, and the variables like to attach themselves a bit to both, but they'll attach themselves more to one than the other. So, this one up here, it's still predominantly attached to me. No, it's not anymore. It's predominantly attached to me, and these 2 are predominantly attached to Zoe. But essentially, what you're trying to do is to work out which variables want to go the most with which factor. So that, in a nutshell, is what you're doing with factor analysis. You're taking some variables like these, and you're seeing whether they want to attach themselves more to one factor or another, and then trying to work out by looking at which variables cluster together. So like there's 2 variables clustered together here, whether there's any sort of substantive meaning to them clustering together. So does it make sense for them to cluster together in terms of what you were measuring? So let's have a look at how to do that in SPSS. Okay, so in terms of doing factor analysis on SPSS, first of all, let's have a look at the data, how the data are laid out. So the example again is taken from my textbook, and it's an example around a questionnaire that measures statistics anxiety called the SAQ. And basically this is a questionnaire. It's got several items on it, and 23 to be precise. And what we're interested in doing is using factor analysis, so as we explained at the beginning, as a way of reducing those 23 items on the questionnaire down to some kind of like underlying factors or components. So that will make interpreting the questionnaire kind of more manageable, because rather than looking at 23 different questions, we can hopefully kind of cluster those questions together into meaningful factors. So in terms of how the data are laid out, if we have a look in the data editor and the data view, each question is set up as a column. So we've got question 1 in column 1, and that question was statistics makes me cry. Question 2, my friends will think I'm stupid for not being able to cope with SPSS. And then question 3, which is in column 3, standard deviations excite me. Well, don't they excite everyone? So we've got each question in a different column, and we've got each, because this was given out to humans, so each participant as a row. So row 1, our first participant gave a 2 on question 1, a 1 on question 2, a 4 on question 3, and so on and so forth. So each of these questions was answered out of 5, and it was a Likert type scale, so with numbers representing agree, disagree. So you can see for each participant we've put in numbers representing their answer on the scale, but I've set up the variables in such a way that we've given labels to those numbers. So if I toggle the value labels, you'll see that all those numbers change to the response on the questionnaire. So participant 1 agreed with question 1, strongly agreed with question 2, disagreed with question 3, agreed with question 4, and so on and so forth. So if we toggle them again, you'll see they just become numbers. So looking in the variable view, you can see we've got a list of 23 questions in this data file. Because I am very, very diligent when I input my data, I've given each question a label to tell me what the question was, and each one has value labels set up. So you can see here a 1 represents strongly agree, a 2 agree, a 3 neither, 4 is disagree, 5 is strongly disagree, and 9 is a value for missing answers. So if they didn't answer the question, we put in a 9. And you can see in the missing values here, we've set up the missing values to tell SPSS when you see a 9, that means they didn't answer for some reason. Maybe they didn't want to admit that standard deviations excite them. Who knows? So that's the basis of how the data's laid out. So we'll go back to the data view. Okay, so in terms of doing the factor analysis, you want to be in the Analyze menu, and it's factor analysis you can find in the dimension reduction part of the Analyze menu. And you can see within that there's an option for factor, which is where you find factor analysis and principal components analysis for that matter. It couldn't really be simpler to do. So we've got our questions listed here on the left hand side of this dialog box. You just select them all, and if they're all in the right order like they are here, you can just whack down the shift key and select them all in one go and transfer them across by clicking on the arrow. So basically, if you clicked on OK now, you would get a sort of a basic factor analysis with default options. However, we'll have a look at a few of the options. Again, the textbook obviously goes into quite ridiculous and meticulous detail about all the options, probably more detail than anyone really cares about. But there's a few important things here for us to consider. So first thing to consider is extraction, or the first sort of big important thing. So what happens is when we do a factor analysis is we're trying to kind of discover what these underlying linear factors might be within the data, and there's different ways of doing it. So one way of doing it is principal components analysis. Another way of doing it, which is different to factor analysis in ways that I won't go into now, the other way to do it is using a factor analysis. And if you do a factor analysis, there are different types of factor analysis you can use. So first of all, you need to choose a method for kind of finding these factors or extracting these factors. So there's lots of different methods you can choose. The default is principal components, but if you want to do kind of a proper factor analysis, then principal axis factoring is a good one to pick. Not that there's anything wrong with the other ones, but principal axis factoring is a pretty common one for people to use. Now what will happen first off is SPSS uses this default option of it basically determines whether a factor is important by the size of its eigenvalue. Now the eigenvalue, horrible word, doesn't mean much to most people, myself included. It's basically a measure of how much variance a factor can explain, so how much variance within the data a factor can kind of chip away at. Mathematically, it means something quite different to that, but essentially that's all it is. It's just a gauge of, if an eigenvalue is big, then it means that factor is explaining a lot of the variance in the data that you're putting in. So by default, SPSS chooses to keep hold of factors that have eigenvalues greater than 1. If you want to read about the whys and wherefores of the value of 1, then read the textbook. But that's a pretty common rule to use. So that's what it will do by default. However, there may be situations where that's not a very good algorithm to use, and especially if you've got big samples, people quite often find it useful to look at a scree plot. And a scree plot is a plot of the eigenvalue against the factor. So you can and it has a very characteristic shape. It looks like the scree of a thing, cliff, whatever. So we should ask for a scree plot, because that's a useful thing to look at, especially if we've got a decent sized sample. And if we look at the scree plot and we decide that we think a different number of factors could be extracted, we can click down here to ask SPSS to extract a particular number of factors that we want. However, for the time being, we're just going to stick with the default and retain all the factors that have eigenvalues greater than 1. So that's the first thing to think about, extraction. The second thing to think about is rotation. So what factor analysis does is it does a sort of first pass at finding these factors, and works out the eigenvalues and comes up with a solution and all the rest of it. But then it can use something called rotation, which is a way of maximising the loadings of variables onto particular factors. Basically, it cleans up, or hope, fingers crossed, it should clean up the answer for you. Again, if you want more detail on rotation, read the book. But essentially, it's a way of kind of manipulating the factors, or sort of shifting them in geometric space to maximise variables' loadings on one factor and minimising the loadings on another factor. So it makes the answer as clear as it can be given the data that you've got. But there's different ways that you can do this rotation. So the first way is orthogonal rotation, and that just means that all your factors are kept independent of each other. If you want to visualise it, it means your factors are at right angles. So orthogonal rotation keeps them independent, whereas oblique rotation allows your factors to correlate with each other. And arguably, especially if you're doing psychology, it would be unusual to think of a situation where you would be doing a factor analysis and you wouldn't expect your factors to correlate, really, because if you're measuring psychological constructs, or a similar pool of psychological constructs with a questionnaire, you'd sort of expect them to correlate with each other. So in sort of real terms, oblique rotation for psychologists especially is probably a more realistic assumption. However, you can sort of pick and choose. So we've got basically Varimax, Equimax, Quartimax are all orthogonal rotations, of which Varimax is the most commonly used one, I think it's probably fair to say. If we wanted to do an oblique rotation, then we would click on direct oblimin, which is an oblique rotation. So those are your two options. In the book chapter, we have a look at what happens with both. But given what I've just said about psychological constructs and how we ought to let them correlate, I'm going to stick with direct oblimin here. So this is doing an oblique rotation. You can get factor scores out of SPSS and save them as variables. I'm not going to do that here. I mean, again, I go into it in the book, but this is just supposed to be a quick guide. And in terms of options, the main options here are, if you've got missing data, you can choose how to deal with it. So you can either, if you've got a case that has any missing data, you can exclude them from the whole analysis. That's what exclude cases listwise mean. You can exclude cases pairwise, which means if a person has a piece of missing data for one variable, it will still include all their other data. It just won't include their data for the variable that they've got missing values on. You can get quite peculiar results when you use when you choose this kind of exclusion by pairwise method. And replacing with the mean is just taking any data and replacing it with the mean value for that particular variable, which again is not that advisable. It's kind of okay if you've got a few missing values, but if you start having lots of missing values, replacing with a mean, all that really does is reduces the variance in each of the variables, so it's not a great thing to do. In terms of the bottom half of the options, there are a couple of useful things. So the first thing is this basically determines how you display the factor loadings, and the factor loadings tell us about how each variable relates to a particular factor. So first of all, we can sort them by size. Now this is quite useful because it means it will list the variables in order of their factor loading, so it just makes the table quite easy to read. The other thing we can do is we can suppress small factor loadings, and although you've got to be a bit careful with this, it can be, because it can give, if you suppress them, basically it means that they don't appear in the table if they're too small, and that can create the impression that that a variable doesn't have a factor loading for a particular factor, because you'll just get a blank space in the table. So you need to remember, if you click on this option, the SPSS is not printing out certain values, but they're still there, but it's just you're not seeing them. So I quite often, well, I say quite often, I never use factor analysis, but when I'm writing books, I think using 0.3 is not bad, as long as you remember that all the factor loadings still exist. So what this will do is it will just clear the table of values that are less than 0.3, which, as we'll see in a minute, can be quite useful. So that will do as a basic set of options. Click on OK. We should hopefully get some output coming up in the output window at some point before my death. So here we go. So the first part of the table, which I'll just double click on it and tidy it up a bit. Alright, there we go. It's a bit easier to see now. It lists all of our questions in our questionnaire, and it tells us the communalities. Now this is basically the shared variance that variable has. And to some extent, we don't really need to interpret this table particularly, although, again, if you look in the book, you can put these values to some good use in terms of determining the rule that you use for factor extraction, but I don't have time to go into that here. We then get a table that tells us about each factor. So we've got 23 questions, and initially it extracts 23 factors, and it works out what the eigenvalue is. So this, as I said, is kind of an estimate of how much variance a factor can explain. And what it does is it uses these to kind of hang on to extract only a small number of factors. So it begins 23 questions, 23 factors. But then it looks at the eigenvalues and says, well, only 4 of them have got values bigger than 1. And that was the criterion it was using. So over here, we've got some new, so it extracts these 4 factors, it keeps hold of them, it discards the rest, throws them in the bin, and then it recomputes the eigenvalues just using these 4 factors. And, basically this kind of just tells you that you've had 4 factors extracted, essentially, and how much the cumulative percentage of variance that you're explaining with those 4 factors. So first factor explains 29% of the variance. If you include the other 2 as well, you're getting up to about 40% of the variance. We can also use the scree plot. So let's, we might be happy for SPSS to extract 4 factors, but we might also want to look at the scree plot to give us some idea of whether that was a reasonable thing to do. Now what we're looking for on the scree plot is the point of inflection. So that's the part of basically where the curve sort of tapers off to a sort of horizontal line. Now looking at this particular scree plot, there's an argument for the point of inflection being at 3 factors. And basically we're looking to retain any factors to the left of that point of inflection. So there's a point of inflection at 3, which would mean retaining or extracting 2 factors, but there's also a point of inflection at 5 factors, which would mean retaining 4. So this is a bit of an ambiguous scree plot, but at least one of the points of inflection seems to correspond with SPSS's decision to extract 4 factors. So there is sort of converging evidence of extracting 4 factors. So that's what we'll do. We won't rerun the analysis. However, if you look at your scree plot, you've got a sample bigger than about 300 and you decide you want a different number of factors extracted to what SPSS has done by default, then basically rerun the analysis and ask it to only select the number of factors that you want. Okay, so moving on, we need to now try to interpret which questions load onto which factors. And when in the options we were talking about listing variables by their loadings and suppressing certain values, we were basically doing that to help us to interpret these tables. Now when you've done an oblique rotation, you'll get 2 tables that we need to interpret. One of them's a pattern matrix and the other one's a structure matrix. And it's slightly, they may give you, it's plausible that they give you different answers, but in theory, you should sort of pretty much see the same thing. So if you have a look at this pattern matrix, which should correspond to the one that you see in the book, if you've got the book, we can start to use this to, I should say, if you've done an orthogonal rotation, this will be called the rotated factor matrix. So what you're looking at doing is seeing which variables load onto which factors, and by suppressing values in this table, I've made it quite easy for you to see. So all these blank spaces ought to have values in, but we know that these values are less than 0.3 because we asked SPSS to suppress values less than 0.3. So we can see, for example, factor 1, what variables loaded highly onto it. It's questions like I wake up under my duvet thinking that I'm trapped under a normal distribution, or I can't sleep for thought of eigenvectors. I weep openly at the mention of central tendency. So these are all kind of statistical things, statistical concepts. So it's kind of a fear of statistical stuff. And we've got like a cluster of them that all seem to have a sort of a common theme. If you have a look at factor 2, we've got items, so this is this sort of block here. We've got items like my friends are better at statistics than me, my friends are better at SPSS than me, my friends will think I'm stupid for not being able to cope with SPSS, if I'm good at statistics my friends will think I'm a nerd, and things like that. So this is all kind of social peer pressure around statistics, and again there's quite obvious sort of common theme between those questions because obviously I made the example up. If we look at factor 3, so this is this block of questions here, we've got items like I have little experience of computers, SPSS always crashes, computers hate me, I worry that I'll cause irreparable damage because of my incompetence with computers. It's very computery, so this factor seems to represent a kind of a fear of computers. And the final factor down here, we've got 3 items that kind of seem to cluster together on factor 4. And these are things like I've never been good at maths, I did badly at maths at school, I slip into a coma whenever I see an equation. So again, these are items that seem to reflect a common theme, which is mathematics. So factor 1 looks like it's kind of a fear of statistics that those questions represent. Factor 2 is around sort of social pressure to do things statistically. Factor 3 seems to be about computers hating you. And factor 4 seems to be around fear of mathematics. So our statistics anxiety questionnaire seems to break down into kind of 4 components of kind of statistics anxiety. One is fear of stats, one is kind of fear of social pressure around stats, one is fear of computers, and one is fear of mathematics. So that's essentially what the factor analysis is doing. We're reducing this questionnaire down to these sort of a smaller number of factors and then trying to interpret which questions load onto which factors, and if they have if the questions that kind of hang together on a similar factor seem to represent similar things, then we might make that leap of faith to suggest that the factor represents some kind of underlying dimension that those questions are all tapping into. For example, fear of computers or fear of mathematics or whatever. So obviously there's a lot more to it than that, which I can't go into in a 15-minute webcast, but hopefully that gives you a bit of a flavour of how to do factor analysis on SPSS. And yes, don't ever feel like you're trapped under your duvet and that it's a multivariate normal distribution trying to crush you to death. Unless, of course, that makes you happy.